Hello again, Mr. Snell here from UK, teaching for Kenyan students mainly, but anybody else who can be interested. In the first program, which was an introduction to moles, what we did was we looked at the three relationship triangles, the three easy in three different colors, ways of calculating moles for the three main ways we measure out chemicals. Masses of solids mainly, but also liquids and gases. Concentration and volume of solutions like hydrochloric acid or sulfuric acid or something like that, copper sulfate, doesn't matter. And then the volume of gases. And in that first program, we came across those three triangles and we did some examples, which you should repeat until you can get them right every time. And that was for the first two triangles, the green and red, the masses and the concentration and volume. And today what we're going to do is we're going to go on to the gases, and we're going to do some examples of gases. And then we're going to look at the experiment, which I hinted at last time, this one. And we're going to see, firstly, we said that we would start with 0.1 grams of magnesium. We would work out whether this or that was going to be in excess. And then we would try to work out and see how much of the hydrogen which is produced is actually produced. So we'll see that. Back to me for a moment. So here is the reminder of the three triangles. If you remember the first chap, I mentioned somebody who came up with this first one. This one was about moles, and we said a nice easy way to remember it is the moles. You have a mole rat if you're in Kenya, or moles if you're in the UK. Moles ram underground. It's obviously not ground or anything like that. It's just a silly way of remembering that. The second one, every solution is given with a concentration of volume, or we're trying to find that from the moles. And in this one here, we said, hey, if we poured the solution onto the ground and the moles were underneath, they drown, so they come up to the top. So the moles are at the top in this one. And the only other two things are down here. We had to divide the volume by 1,000 because most of our volumes in calculations are given in cubic centimeters. Because this is in moles per cubic decimeter or liter, this also has to be in cubic decimeters or liters. So to turn cubic centimeters into cubic decimeters, we divide by 1,000. The gases one is the same sort of shape as the solids one in that the moles is at the bottom. And just like the solids one, where you never have to remember the RAM or RMM, here, there's a number here which you will always be given in the question. Now this question, this volume here is the volume of 1 mole of the gas at around about room temperature. Now, it's normally a slightly warmer temperature than we have in the UK a lot of the time. This would be smaller if it was a colder day and larger if it was a warmer day. So sometimes they give it at STP. STP is at temperature, normal pressure, 1 atmosphere, but it's at 0 degrees Celsius. And this number then is 22,400. You don't have to worry about it though, because whatever they want you to use, they're going to give you it in the question. So these three triangles allow us to work out just about everything. All we've got to do is to remember to stay calm in an exam. Go, okay, is it a solid? Is it something where I've got a mass? Is it a solution? If it's a solution, I should have a concentration or a volume, or I'm given some moles and say the volume and I ask the concentration, that sort of thing. Or is it a gas? If it's a gas, I can use this third triangle. With those three triangles, I can do absolutely everything. So I'm now going to share my screen and I'm going to go to the end of the PowerPoint, which we were using last time. And we're going to look at that. Here it is. This is the volumes of gases one. And I mentioned here that the volume of any gas, which is quite interesting if you think about it, that all gases have the same sort of volume under normal conditions anyway. And that's 24 cubic decimeters or 24,000 cubic centimeters here. Moles at the bottom, the volume of the gas at the top, and 24,000 or 24 cubic decimeters at the bottom here. That's the bit I said you will be provided with that. So let's have a look at some examples. They come in all sorts of types at A-level or Form 4 examinations. So I'm going to leave this on. I'm just going to ask you just to pause this for just a moment and have a go at these questions. I'll just go through them and make sure it makes sense. How many moles of nitrogen are there in 2.4 cubic decimeters? Now, because this is in cubic decimeters, we would use the value here, 24 cubic decimeters, not the 24,000. In this one, how many moles in 1 cubic meter? Oh gosh, a cubic meter. Well, now we're going to have to work out how many cubic decimeters or how many cubic centimeters there are in 1 cubic meter. So we'll come down to that in just a minute. Then we says, if it has 6 grams of hydrogen, what volume would it take up? Wait a minute. Grams, that means I'm going to have to use the first triangle to work out the moles, and then that will allow me to use the third triangle to work out what the volume is. And this one here is even more complicated. It says 2.2 grams of X, whatever X is, has a volume of that. What is its molar mass? Now, in this one here, we're going to be using the third triangle to work out how many moles that is, and then use the first triangle to say, okay, now I've got the moles, I've got the mass. What is the molar mass? What is the RMM? And if you're really sharp, what could it be? Let's just go back to this bit here. How many moles are there? Sorry, how many cubic decimeters or cubic centimeters are there in a cubic meter? You need to be able to work that out. So here we go. Well, you have to be able to remember how to do it. So we're talking gases in this one, remember? A cubic meter, this is obviously not a cubic meter. This is a cubic, this is just a cube, rather badly drawn. So if this was 1 meter cubed, that is 100 centimeters across here, 100 here, and 100 here. So in terms of cubic centimeters, it would be 100 centimeters times 100 centimeters times 100 centimeters. Ah, okay, 100 times 100 times 100. That looks a lot like a million. Now, if 1 dm cubed is 1,000 cubic centimeters, then just think how many cubic decimeters there must be in a cubic meter. Okay, so 1 cubic meter is 1,000 cubic centimeters, sorry, 1 million cubic centimeters. And if 1 cubic decimeter is 1,000 cubic centimeters, then 1 meter cubed is 1,000 cubic decimeters. It is very unlikely that you will be asked to do a calculation involving this without them telling you that. For kilograms and grams, they don't have to tell you that. They assume that you know 1 kilogram is 1,000 grams. But in this one here, 1 cubic meter, this they would probably tell you anyway. But I'm just doing it there so you can do the question. So what we're going to do is go back to the other screen. And what I'd like you to do is to just have a go at this set of questions. So I'm going to ask you just to pause the video and write down the question and then have a go at the answers. And in just a moment, I'll stop talking. And at that point, you're going to have to stop the video and then you can have a go at them and I will then give you the answers. So pause it now. And here are the answers. Whoops, that's gone the wrong way. Oh, hello. Oh, there we are. So in the first one, we were asked what 2.4 cubic decimeters was, and that's 2.4 over 24. That's 0.1. Give yourself 2 marks. A cubic meter, we said, was 1,000 cubic decimeters, or, excuse me, or, yes, so we have 1,000 cubic decimeters over 24, or a million over 24,000, and it comes out the same, which is 41 2/3, 41 at 0.67 moles. 6 grams of hydrogen using the first triangle. Hydrogen goes around in pairs. It's a diatomic molecule. So 6 over the mass of 1 H2, which is 2, is 3. So it's 3 moles. 3 moles times 24 is 72. The last one is a bit more confusing. It starts with 1.2 cubic decimeters. So you work out how many moles that was. 1.2 divided by 24. This is using the third triangle, is 0.05 moles. And then it told you in the question that that volume had a mass of 2.2 grams. So if 0.05 moles has a mass of that, then we can put it into the first triangle where moles are underground, moles ram underground. So I've got the moles here, I've got the grams, which goes at the top. So the RMM is going to be that over that, which comes out as 44. Anybody got any idea what it is? Yep. It's carbon dioxide. Okay. So here are some proper examination questions, which I'm going to let you have a go at just later. And it's one very much like the one I'm just about to do, but we're going to do a little experiment now. So that's what we're going to do. So, and then you can have a go at this question afterwards. I'm just going to show you the question. Then you can pause this at some point and write it down. But we're doing exactly what I'm going to do. Oh, hello, what's happened there? I'm going to do the little experiment in just a minute. We got 0.1 grams of magnesium, 50 cubic centimeters of, that's an O, 1 mole per cubic decimeter, H2SO4. And the questions are, which is in excess? In other words, which one will be left over? How many moles of H2 should be produced? We'll talk about why it might not be completely. And then what volume would that hydrogen be? So I'm going to stop sharing now. We're going to have a look at the other camera. So here we go. Okay. So here I have my, let's move this a little bit closer. So I've got here my 0.1 grams of magnesium. I measured out using a measuring standard, not terribly accurately, but that's okay, not very precisely, for a reason you'll see in just a minute. So I've got 50 cubic centimeters of the sulfuric acid here. They react 1-to-1. Mg plus H2SO4 goes to MgSO4 and H2. You probably know that anyway. So what I'm going to do is I'm now going to angle this a bit. Hopefully you'll be able to see it a bit better. Okay, get that out of the way. And what I'm going to do is I'm going to do something which is a little bit difficult to do, which is to start with that in. Whoops, good heavens. I'm going to put the magnesium into the conical flask. I'm going to put the top on and hopefully start the reaction all at once. Okay, so I'm going to try to get all these bits and drop them all in together. They're okay to handle. It's magnesium, it's not a problem. So I'm going to put them all in and put the top on and hope to capture all the gas which is produced. Oh no, one's dropped out. Oh no, terrible. So you hopefully can see it fizzing. It would be easier if it was against a darker background. It is fizzing. It's got a darker background. There we are fizzing. And what you should be able to see over here is that the plunger is being pushed out. Now the magnesium is reacting pretty well. And the plunger is being pushed out. There's not much magnesium left already. It's going very fast. Fizzing, and we're getting, let's see if we can get a little bit closer on that so you can see it finishing off. Oops. There we are. You can see all the mistiness in there and the bubbling of the last little bits and pieces. And that's it. Now let's have a look at the volume of the gas produced. So I'm coming over to the gas syringe and let's see if we can focus that just a little bit. There we are. And what it's saying is that it is just over 100 cubic centimeters. Just over 100 cubic centimeters. So my 0.1 grams of magnesium and my sulfuric acid, 50 cubic centimeters of 1 mole per cubic decimeter. They have reacted and produced that amount of hydrogen. Sorry, I'm just scrabbling around looking for something. Okay, so let's come back to me. Let's see if we can work this out. So here we are. Let's have a look at the calculation. So we've got the equation Mg plus H2SO4 goes to MgSO4 and H2. That's the gas. From the first triangle, because that's the one that we use, I've got 0.1 grams here. In the second, I'm going to use the second triangle here. I've got 50 cubic centimeters of 1 mole per cubic decimeter. And it seems to have produced 100 and a little bit cubic centimeters. And when we do the calculation, you'll probably find that, well, the problem with this, the reason why that's just over, is that I used a relatively imprecise balance. That means it was only 2 decimal places and it said 0.10, but it was, this is pretty approximate. When you're weighing out this amount, you might get it just a little bit wrong. I was hoping it would be exactly 100, which would have been nice, but it isn't quite. And that's probably because I had just a little bit more of that than I expected. So let's have a look at the calculation properly. I'm going to share my screen again. You can have a look at it. And you can try and have a go at the calculations. So here we are. This is the question. Here it is. It's on my board as well, of course. Which is in excess? How many moles of H2 should be produced? And what volume will that be? So what I'd like you to do is I'd like you to pause it just now and see if you can work that out. Start with the first triangle for that, the second triangle for this, and then that should allow you to look at the equation. One of these there'll be much more of. There'll be lots of it left over, one of them. So then you look at the other one and you decide how much hydrogen we produce because it's 1 to 1. And then work out using the third triangle what happens here. So pause it now and try and work it out. Okay, let's have a look at it. So here we are. Here's the equation. Here's the amounts. These are the 3 questions. Which is in excess? How many moles of hydrogen? What volume of hydrogen? Here's the first bit. Well, I color them with the color of the triangles. You might not have noticed for those of you in Kenya, but I'm using green and red and black, and that is a Kenyan set of colors. So the first triangle for the mass of the magnesium, if we look on a periodic table, the mass of magnesium, the RAM, the RAM of magnesium is 24. So 0.1 divided by 24 is 0.00416 moles. The sulfuric acid, we were given a concentration and a volume. The concentration was 1. The volume was 50 cubic centimeters, so it's 50 over 1,000, which comes out as 0.05. And that means that the excess, this is a larger number than this one, and therefore there will be lots of acid left over. And you did see that all of the magnesium disappeared. The second part of it is how many moles of hydrogen would be produced? Well, if there's less of the magnesium than there is of the sulfuric acid, then it all depends on how much magnesium I've got. 1 magnesium will produce 1 hydrogen, otherwise it would be a number here, 2 or 3 or whatever. So 0.00416 of this will produce the same amount of that. So we get that. If you got that, you've done very well indeed. Why don't we use the moles of H2SO4? Because that's the one we've just worked out is in excess. and therefore is going to be left over. And the last question, what volume of hydrogen will that be? From the third triangle, where the moles are at the bottom and the volume is at the top, and 24,000 or 24 cubic decimeters is at the bottom right. 1 mole of gas is 24,000 cubic centimeters. So 0.00416 is that times 24,000, which is 100 cubic centimeters, which is what we found in the experiment, just about right. Now, here are some more examples of examination questions taken from both English and Kenyan papers, or British and Kenyan papers. And I'd like you to have a go at these. They're the same sort of thing. The first one is which chemical is in excess. And the second one here is how much volume of gas will be produced. Okay, I'd like you to have a go at those. Pause the video now, and I will then show you the answers afterwards. And here are the answers. So in the first bit, 1A, which one is in excess? The mass of the Mg, sorry, the zinc in this case, my apologies, 1.96. So we use the first triangle. The mass of zinc is 65.4. If your periodic table told you it was 65, that's fine. You just use 65. It's 65.4, but sometimes they approximate. So that would give me 0.03 moles. My hydrochloric acid is 100 cubic centimeters of 0.2. So I've got my concentration times my volume over 1,000, which comes out as 0.02. So the zinc is the larger number, zinc in excess. 2 marks. Nice. When you think about it, if you've only just started really getting to grips with moles, this is quite a hard question. And lots of people won't be getting it right. So it's good that you're getting it right. Here's the second bit. Finding the volume of the H2 gas. It's the third triangle. Now, because from this equation, what we worked out to start with was that the zinc was in excess, we're starting with the number of moles of the hydrochloric acid. So we start here and we can see that 2 moles of HCl produce 1 of H2. That number in the front there, 2 HCl makes 1 H2. Here we are. Now the moles of HCl was 0.02. So the moles of H2, 2 to 1, will be half as much. 0.02 becomes 0.01, and the volume will be 0.01 times 22.4, which is 0.224 cubic decimeters, because the question said, here we are, there's the zinc RAM, and that, they said this is the volume, liters or cubic decimeters at STP. That's the standard temperature and pressure, in other words, 0 degrees. If you're in Kenya, that'd be an unusual temperature for you to get to. So there, that's another 2 marks. Well done. Here's another question which you can have a go at. You'll have to pause it in just a minute so that you can see it. Zinc sulfate is sometimes used to help people who have a zinc deficiency. And the zinc sulfate which you buy has got waters of crystallization attached to it. There's a way of working out how many waters of crystallization. And basically what happens is this, as it says in part A, a technician carefully heated the crystals, slowly, gently, until it loses all the water, because the water gets boiled off. So 3.715 grams of the magnesium with the water ends up at 2.08. Okay? So the difference between that and that is the water. So how many moles of zinc sulfate are there in that? And that will allow you to work it out. Okay? Have a look. Pause the video. Write down the question. Have a go. This is a hard question. And here's the solution. Oops, where's the solution gone? Here we are. My apologies. I went through several pages. Here's the moles of zinc sulfate. Right, we have 2.08. We put that over the mass of this, which is 65.4 plus 32 plus 4 16s, which are 161, and that's the moles of the zinc sulfate. Because 1 mole of zinc sulfate contains 1 zinc, so the moles of zinc will be exactly the same as the moles of zinc sulfate. Now, the moles of water are, the mass of water is the original mass minus the dried out mass, which is 1.635. So you take the original mass and take away from it the dried out, or what we call anhydrous, and it's 1.635. So the moles of water is 1.635 over the RMM of water, which is 18, 0.0908. Now, what we want to do now is to look at what the ratio of these two is. Whenever you've got two numbers and you want to find the ratio, you divide through by the smaller one. So this one is the smaller one. Divide this by itself and it becomes 1. So the moles of zinc is 1 and the moles of water is 0.0908 divided by that, and that is 7. So the number of waters of crystallization is 7. That's a really hard question. There are some other questions which we're going to do next time, which are to do with empirical and molecular formula. But for now, that's the end. So I'm going to say goodbye. Try and do those calculations. Look through them several times. The more times you look through them, the simpler they are. Okay, so good luck and get on with chemistry.